am Sushanto. In this session, I will find Thevenin and Thevenin of this network. Now, first of all, we have to check if we can use Thevenin's theorem for this network. Now, this network is purely resistive network with a dependent voltage source whose EMF is proportional to some current. So, clearly it is a linear network. So, as it is a linear network, so this network can be reduced as one voltage source with EMF Thevenin and a resistance Thevenin. Now, this network does not have any independent voltage or current source. That is why its Thevenin is 0. So, we have to short circuit this voltage source. So, I short circuit this. Therefore, the equivalent circuit is reduced to just a resistance. So, our goal here is to reduce this network into one resistance Thevenin. So, you have to find Thevenin, that is it. Now, how to find Thevenin? So, for that we have to supply a test current 1 ampere, and for that we have to include one current source here. So, I include one current source supplying 1 ampere to the network. So, this is connected across AB. So, this is the test current. Now, suppose the potential difference between P and Q is V. So, I assign a voltage V here and I ground the point Q. So, this has got a voltage equal to 0. So, as Q is grounded, N is also grounded. So, both N and Q have a potential equal to 0. So, as this potential is 0, so this potential of the potential of this point is 1.5 I. Now, I in this case is minus 1 because I is flowing in this direction and actually the current is flowing in this direction. So, I is equal to minus 1. So, potential at this point is 1.5 times minus 1. Now, assume that the current through this is I1 and the current through this is I2. So, if I apply KCL at P, I see that 1 ampere is entering P and I1 and I2 are exiting P. So, I1 plus I2 is equal to 1 ampere. Now, I1 is equal to potential of P, that is V, minus potential at this point 1.5 times minus 1 divided by the resistance, that is 3 ohm, and I2 is equal to potential at this point, that is V, minus potential at this point, which is 0, divided by 2, and that is equal to 1. So, V over 3, now this is minus and minus plus, so plus 1.5 over 3, which is 0.5, plus V over 2 is equal to 1. Now, I send 0.5 to this side and we add V over 3 and V over 2. So, we get 2V over 6 plus 3V over 6 is equal to 0.5. So, 3 plus 2, that is 5, V over 6 is equal to 0.5. So, V is equal to 6 times 0.5 over 5. So, this is 0.6 volt. So, V is equal to 0.6 volt. Now, if we look at this circuit, which is equivalent to this one, the V, that is the potential difference between these 2 points, is 0.6 volt. So, this is 0.6 volt. So, this is 0.6 volt and a current 1 ampere is flowing into this. So, when 1 ampere is sent to this circuit, the potential difference that is developed between A and B is 0.6 volts. So 0.6 is equal to 1 times R Thevenin. So 0.6 is equal to 1 times R Thevenin. So R Thevenin is equal to 0.6 ohm. So the Thevenin resistance of this circuit is 0.6 ohm and the Thevenin voltage of this is 0 volt. That is what we found using Thevenin's theorem on this network.